Duxford, England, January 1942. An intelligence officer sits at a table with a stack of accident reports and begins reading the numbers aloud. The room is not responding to combat losses. Every man present understands combat losses. You accept them, record them, use them to improve tactics. What is being read from those reports is something different, something harder to accept, something that no operational commander can defend to a pilot climbing into a cockpit before dawn. In the preceding 4 months, more British fighter pilots have been killed by mechanical failure than by German guns. The aircraft in question has been in squadron service since September, less than half a year, and it is killing its own men at a rate that the meeting is struggling to classify, because there is no classification for an aircraft that is more dangerous to its crew than the enemy it was built to defeat. The aircraft is the Hawker Typhoon. The engine beneath its chin radiator is the Napier Sabre, 24 cylinders, 2 crankshafts, 3,700 revolutions per minute, 2,200 horsepower from 36 litres of displacement, 1 horsepower per pound of engine weight, the specific power figure that every engine designer in Britain had been chasing for a decade. And it is not working, not in the way an engine occasionally fails. The Sabre was seizing in flight without warning. It was igniting during ground start. The ground crews kept fire extinguishers beside every Typhoon during every engine start, because the alternative was watching the aircraft burn before it reached the runway. Carbon monoxide was bleeding from the engine into the cockpit at altitude. And the only reason more pilots were not losing consciousness over the English Channel is that the standing order required all Typhoon pilots to wear oxygen masks continuously, regardless of altitude, regardless of mission profile. The engine vibrated so severely at certain power settings that pilots could not rest a hand against the cockpit structure without the vibration transmitting through their bones. The high-pitched note of 24 cylinders firing at combat RPM was unlike anything else in the RAF inventory. Not the deep throb of a radial, not the smooth surge of a Merlin, a sound that pilots described as fatiguing in itself, a mechanical scream that sat at a frequency the human auditory system registers as distress. And the tails were coming off. The engine's vibration signature was coupling with a structural resonance in the Typhoon's rear fuselage, exciting a flutter mode that the airframe had not been designed to survive at combat dive speeds. Several Typhoons had lost their complete tail assemblies in high-speed dives. The empennage simply departed. The aircraft did not recover. The pilot did not survive. The men in that room at Duxford were conducting the arithmetic of a decision that every person present understood the weight of. Ground every Typhoon in Britain, cancel the program, walk away from 2,200 horsepower and admit that the most powerful fighter engine the country had ever put into production was not, in its current state, compatible with keeping pilots alive. They did not cancel it. The reasons why, and the cost of not cancelling it, and the institutional failure that had produced the crisis in the first place, and what the Sabre eventually became after that failure was corrected over Napier's objections. That is what this story is about. But before the failure, the machine. Because you cannot understand what went wrong in 1942 without understanding what Napier had actually built. And what they had built was a mechanism so precise, so geometrically ambitious, so unlike every other production aircraft engine in the world, that the gap between the hand-assembled prototype and the factory production line was not a gap of engineering confidence. It was a gap of manufacturing capability that nobody at Napier had fully assessed before the program was committed. No poppet valves, not one. In 24 cylinders of the most powerful inline engine ever put into British production, there was not a single conventional valve of the type that had controlled gas flow in every production piston engine since the 1880s. Harry Ricardo had explained why this was necessary in 1927. Ricardo was the most respected internal combustion engineer in Britain, and his study of that year read, in the industry, as a verdict. Traditional poppet valve engines, Ricardo concluded, were unlikely to produce much more than 1,500 horsepower. The geometry of the poppet valve, the spring-loaded disc that opens against combustion pressure, closes against its seat, and repeats this cycle at several thousand times per minute, had been refined toward a physical limit. The valve needed time to open, time to close, time to seal. At the rotational speeds required for 2,000 horsepower from a compact displacement, the valve's own mass became a problem that metallurgy could not solve and spring rates could not correct. The flow restriction at the port became a ceiling that the valve's shape would not allow the designer to raise. The ceiling, Ricardo wrote, was 1,500 horsepower. The Air Ministry in 1935 required 2,000. Frank Halford sat in his London office, close enough to Ricardo's that the two men could have walked to lunch together in 10 minutes. and went looking for a way through the ceiling that Ricardo had drawn. Halford had been working for Napier since the 1920s, designing the H-16 Rapier and the H-24 Dagger, building his reputation on engines of increasing complexity and performance. He understood Ricardo's ceiling. He also understood Ricardo's recommendation, which was contained in the same study that described the limit: the sleeve valve. Not a new concept. The Scottish company Argyll had used sleeve valves in its cars before the First World War. Bristol had been developing sleeve valve radial engines in collaboration with Ricardo since 1932, but nobody had built a sleeve valve engine at the power density, the cylinder configuration, and the production scale that Halford was proposing to Napier's board in 1935, and then to the Air Ministry shortly after. A cylinder within a cylinder, a steel sleeve sitting in the bore between the cylinder wall and the piston, ports, machined holes, cut through both the sleeve and the cylinder wall at specific positions. The sleeve moves. As it moves, its ports align with the cylinder wall's ports. Mixture flows in. Combustion occurs. The sleeve moves again, differently. Exhaust ports align. Burned gases exit. No spring, no disc, no conventional valve mechanism at any point in the cycle. Gas flow controlled entirely by the geometry of a moving tube. In the Napier Sabre, the sleeve does not simply slide. It executes two motions simultaneously, driven by a worm gear eccentric shaft running at half crankshaft speed, channeled through 24 individual eccentrics connected via bronze worm wheels. 11-tooth worm gears driving 22-tooth wheels, the compound reduction built specifically to achieve the precise half-speed ratio the sleeve timing required. The sleeve reciprocates along the cylinder axis, approximately 2.5 inches of linear travel, and simultaneously it oscillates, rotating approximately 56 degrees around the same axis. The combination of those two motions, phased to the crankshaft position by the driveshaft geometry, causes the intake ports to open 40 degrees before top dead center and close 65 degrees after bottom, and the exhaust ports to open 65 degrees before bottom dead center and close 40 degrees after top. 24 cylinders, 24 sleeves executing this compound motion continuously for every second the engine runs. The H-block configuration placed 4 banks of 6 cylinders, upper left, upper right, lower right, around 2 crankshafts positioned one above the other and geared together at the propeller end through compound helical reduction, gearing at a ratio of 0.274 to 1. Because the cylinder banks opposed each other, their inertial forces cancelled. First-order vibration, eliminated by geometry. Second-order vibration, eliminated by geometry. The result was an engine that produced less vibration per unit of power than almost any contemporary design, smooth by the standards of what it was, which was the most mechanically ambitious production aircraft engine Britain had ever attempted. 36 litres, 2,200 horsepower, 2,360 pounds dry, 82 inches long, 40 inches wide, 46 inches tall, smaller than its competitors, producing more power than its competitors, and burning fuel at a rate of consumption that made long-range operation genuinely viable. On the test stand at Napier's Acton facility on 17 January 1938, the first prototype Sabre ran under its own power, limited to 1,350 horsepower for safety. By March 1938, it was passing tests at 2,050. By June 1940, it had completed the Air Ministry's 100-hour type test at 2,200 horsepower. Frank Halford had delivered the promise. Then Napier tried to build it at scale, and every assumption that had held during hand assembly began, one by one, to fail. The prototype engines had been assembled by Napier craftsmen, matched components, fitted individually, adjusted by hand until the clearances were correct. The specific roundness of each sleeve, the specific clearance between sleeve and bore, the specific phasing of the eccentric drive, these parameters had been achieved through skilled fitting, not through dimensional specification alone. A craftsman fits to a result. A production line fits to a drawing. The sleeves were manufactured from chrome molybdenum steel. Under hand assembly conditions, with matched fitting at every stage, the chrome molybdenum sleeve worked. Under production conditions, standardized parts, interchangeable components, assembly at factory pace, the chrome molybdenum sleeve did not hold its shape across the thermal cycle of operation. The heat of running at full power and the cooling of shutdown distorted the sleeve's geometry. A sleeve that was nominally round to production tolerances was not round to the tolerance the bore required. The sleeve dragged, the sleeve bound, the sleeve seized. When a Sabre sleeve seized, the event was not gradual. There was no warning gauge, no progressive symptom, no opportunity to reduce power and manage the failure to a controlled outcome. The sleeve stopped moving, the engine stopped producing power. And if this happened at low altitude, at a point in the flight from which a dead stick landing was not achievable, the pilot's options were limited to the altitude remaining. Napier engineers began testing alternative materials. Chrome molybdenum proved inadequate. They moved to different steel specifications. They tried different heat treatments. They tried different surface finishes, lapping, grinding, honing to closer tolerances. They tried nitriding the sleeves in their own facilities, using processes adapted from other manufacturing contexts. 18 different material and process combinations were evaluated over the course of the program's worst period. Some held longer than others, none held reliably enough. A Gloucester test pilot was killed. A production Typhoon went down over the channel. The sole prototype of the Martin Baker MB3, one of the most promising British fighter designs of the war years, an aircraft that the Air Ministry considered a serious candidate for production, was destroyed when its sabre sleeve failed in flight. The test pilot, Captain Valentine Baker, the co-founder of Martin Baker, was killed in the crash. The MB3 program ended with him. Fighter Command was not simply reviewing the data. Fighter Command was forming a recommendation. 3 seconds, 2, 1. The Bristol Aeroplane Company manufactured sleeve valve aircraft engines from a factory producing the Taurus radial. The Taurus cylinder bore was 5 inches. The Napier Sabre cylinder bore was 5 inches. The dimensions were identical. And Bristol, working with Ricardo since 1932, had solved the sleeve problem that Napier had not solved. Bristol cast their sleeves centrifugally from austenitic steel, an alloy of nickel, chromium and manganese, whose thermal stability under the temperature cycling of engine operation was demonstrably superior to the chrome molybdenum that Napier was using. The centrifugal casting process produced a sleeve whose material density was consistent from wall to wall, without the directional grain structure that forged or rolled steel introduced. After machining, the sleeves were nitrided, nitrogen driven into the surface under controlled heat to create a hardened outer layer of exceptional wear resistance. The finished sleeves were ground to a roundness tolerance of 2/10,000ths of an inch, not approximately, not as a target, as a production standard that Bristol's manufacturing process could hold consistently. Napier knew about Bristol's process. The Ministry of Aircraft Production knew that Napier knew, and through 1941 and into 1942, as the accident reports accumulated, Napier declined to engage. The documentation of the period is not ambiguous about the reasoning. Napier was D. Napier and Son, a precision engineering company with a history extending back to 1808, a company that had built the Napier Lion, the engine that powered the Supermarine S4, S5, and S6 Schneider Trophy racers of the 1920s, the engine that had set land speed records in Campbell's Bluebird. Napier's identity was built on the premise that it built things others could not, that it solved problems others had not solved. Accepting Bristol's metallurgy meant acknowledging, formally and institutionally, that a competitor had achieved in production what Napier's engineers had not. The corporate culture of a company that had won Schneider Trophy races was not structured to make that acknowledgement. Francis Rodwell Banks held the position of Director of Engine Production at the Ministry of Aircraft Production. Banks had spent a career in aero-engine fuel and development work, had managed the fuel supply for the Schneider Trophy races, understood engine metallurgy at the level of practical application rather than theoretical study. He read the accident reports. He looked at the timeline of Napier's internal materials testing program. He assessed how much longer the program could continue to produce the numbers that the Duxford meeting had reviewed. Banks went directly to Bristol. He arranged for Bristol to machine a pair of sleeves to the Taurus specification. Austenitic steel, centrifugal cast, nitrided, ground to 2/10,000ths, for installation in a 2-cylinder Sabre test engine. He did this without Napier's cooperation, around Napier's objections, using the authority of a ministry that held ultimate jurisdiction over a wartime manufacturer that was failing a critical program. The Bristol sleeves ran. The Bristol sleeves completed the test without seizure. The Bristol sleeves were the answer that Napier had been unable to produce and unwilling to accept. Napier adopted the Bristol manufacturing process. Production of compliant sleeves began. By mid-1943, the Typhoon's engine failures had reduced to levels consistent with normal operational wear, rather than fundamental manufacturing defect. The carbon monoxide problem was addressed through cockpit sealing modifications. The tail failures were resolved through structural reinforcement. Fish plates added externally at the rear fuselage joint. Flutter modes damped through mass balance adjustments to the elevator. The Typhoon became what the design had always promised it could be, and that should have been the complete accounting of what Napier's institutional pride had cost. Months of avoidable deaths, a cancelled fighter program. A wartime crisis resolved only when an outside official bypassed the company that built the engine to force an answer the company refused to find on its own. That should have been everything. It was not. By the autumn of 1943, the Typhoon was operational in the role it would define. Not a high-altitude interceptor, the thick wing that had been necessary to accommodate the Sabre's bulk cost too much performance above 15,000 feet, and the Focke-Wulf 190 was faster at altitude. But at low level, below 10,000 feet, with rockets and bombs and 420mm cannon, there was nothing the Luftwaffe could do to it that the Sabre could not fly away from. The Typhoon became a train destroyer, a bridge breaker, a column stopper. By the winter of 1943, it was averaging 150 German locomotives per month across the French and Belgian rail network. By D-Day, 26 Typhoon squadrons were operating with the 2nd Tactical Air Force, the largest ground attack concentration in RAF history. 18 of those 26 were assigned solely to the ground attack mission. At Falaise, in August 1944, the German 7th Army was attempting to break out of encirclement through a corridor less than 20 miles wide. The Typhoons closed it, not metaphorically, physically, rockets tracking flat across the Normandy landscape, into armor, into transport, into the compressed and retreating columns of an army that had run out of sky to hide under. The road between Falaise and Argentan, photographed from the air in the days after the pocket closed, looked like a scrapyard. Tanks, half-tracks, artillery pieces, supply wagons. Abandoned and destroyed in a density that aerial reconnaissance photographers had not seen before on the Western Front. Nearly 200,000 rockets fired by Typhoon squadrons across the Northwest Europe campaign. The Tempest Fair, the Sabre's other primary installation, was doing something even more improbable in the summer of 1944. It was killing V-1 flying bombs. The Fieseler Phi 103 pulse jet weapon flew at approximately 400 miles per hour at low altitude. The Tempest matched it. Between June and August 1944, Tempest pilots claimed 800 of the 1,771 V-1s shot down by the RAF. The New Church Wing alone claimed 638. And as the European campaign moved toward its conclusion, Tempest squadrons encountered the Messerschmitt Me-262 in combat. The world's first operational jet fighter. They shot down 20 confirmed Me-262s before the war ended. A piston-engine killing jet. The Sabre at 2,200 horsepower, in an airframe with a thin wing and a low-drag profile, producing enough speed at low altitude to engage the leading edge of the jet age and win. And the Sabre was still accelerating. The Sabre 7, designation E121, incorporated water methanol injection, a mixture injected into the intake manifold under high boost conditions to suppress detonation and allow manifold pressures that the earlier marks could not sustain. The result was a combat power rating of 3,055 horsepower at 3,850 revolutions per minute and a takeoff rating with maximum injection of 3,500 horsepower. The Hawker Fury prototype, serial LA610, was fitted with the Sabre 7 and reached approximately 485 miles per hour in level flight in 1945, the fastest piston-engined aircraft Hawker had ever built. The fastest British military aircraft that did not use a jet engine, and the trajectory was not finished. The Sabre 8, designation E122, two-stage, three-speed supercharger to maintain charge density at altitudes where the single-stage Sabre 7 lost pressure. Contra-rotating propellers to absorb torque at power levels, that a single-rotation propeller was approaching its aerodynamic limits, to handle without prohibitive penalties in yaw. Bulk fuel injection throughout the operating range, rather than the carburetor-based system retained in earlier marks. Structural reinforcement throughout to handle loads that the Sabre 7's highest power settings were beginning to approach the margins of. Baseline power at 3,350 horsepower, the projected ceiling, documented in Aero Digest in 1946, placed at well over 4,000 horsepower, from 36 litres, from an engine that had first run in 1937 at 1,350. The Sabre 8 was never built. The substantial Sabre 7 production order was cancelled as the war ended. The E122 development was terminated before a single prototype was assembled. And between 1945 and 1950, the majority of Napier Sabre engines in existence were stripped from their aircraft and scrapped. The metal returned to industry. The sleeves, the austenitic steel Bristol sleeves that had finally made the engine work, melted back into feedstock. In December 1942, 3 years before any of this, the British government had forced D. Napier and Son into the English Electric Group. The management crisis, the production failures, the sleeves that had required a ministry official to bypass the company to fix, had been enough. The independent Napier board was dissolved. Frank Halford, whose design the Sabre fundamentally was, departed the company following the takeover. Development from 1943 onward was conducted by Napier engineers working inside a conglomerate that had inherited the program rather than conceived it. When the war ended and jet engines provided an exit from the complexity and the institutional overhead of maintaining a specialist piston engine program, The government that had been forced to rescue Napier in 1942 did not fight to preserve it. The company had spent its credibility. The program had spent its political protection. The Sabre 7 order was administratively convenient to cancel. The E-122 was not yet at the stage where cancellation required explaining to anyone that something real was being lost. Approximately 12 Napier Sabre engines survive in the world. The Hawker Typhoon Preservation Group has a Sabre 2IA. The work to restore a Typhoon to flying condition continues, sustained by a community of engineers and enthusiasts who have spent years learning what the Napier workforce knew and what the English Electric acquisition and the post-war scrapping program came within a generation of erasing entirely. The Sabre 8 exists in one place. A paragraph in Aero Digest, Volume 53, 1946. One paragraph. The extreme limit of power for the E-122 was placed at well over 4,000 horsepower. The paragraph does not describe a fantasy. It describes a cancelled program. There is a difference between what could not be built and what was not built. The Sabre 8 was the second kind. The materials existed. The engineering capability existed. The trajectory from the Sabre 1 to the Sabre 7 to the E-122 was not speculative. It was the product of a development program that had already multiplied the engine's output by a factor of 2.5 and was showing no sign of approaching a fundamental limit. What did not exist by 1945 was an institution with the standing, the government trust, and the post-war industrial mandate to push it through. The engine that refused to run killed its own pilots in 1942. Because the company that built it would not accept a competitor's answer to a problem it had created. The engine that refused to run broke the German 7th Army at Falaise in 1944 because it finally ran the way it had been designed to run. And the engine that reached 3,500 horsepower in 1945, that was approaching 4,000 in the design specification of its next mark, was cancelled not because it had failed, but because the institution behind it had failed first, 3 years earlier, and the account had come due. The Hawker Fury prototype is in a photograph. Silver finish. The Sabre 7 behind that distinctive Hawker nose cowling, 485 miles per hour. The fastest thing with a piston engine that Britain ever flew. It is not the Sabre 8. The Sabre 8 is a paragraph. Every number in that paragraph is real. None of them were ever tested in the air.